So at step 4, Dijkstra will have added node E. And if we continue at step 5, not surprisingly, it will add node D, which causes no change to the data structure because D has no neighbor not already added. And so the last step will be to add B, and therefore this is the final step. We see that one feature of Dijkstra is that at every step, it adds a node, and for this node, things will never be changed later in the algorithm. When we had added node E, for example, any further step did not modify the shortest path and the distance to node E. This is what is called a greedy algorithm. At every step, it computes something, and that is the final value for that thing that has been added. The fact that there is a greedy shortest path algorithm is the beauty of Mr. Dijkstra, who found it. We will see that distance vector uses another algorithm called Bellman-Ford, which is not greedy at every step. It improves the distances, but it's only at the very end that we know what the final distance is. Here, as soon as a node is added to the graph, we have the final value. What do we distill out of this? Well, only the path computation. So once we have done this, we can know how to go from A to D. Remember, all of this is done at one node, A, for example. In order to go to D, then what we can do is simply follow the red lines in the reverse direction. So we will know that from A to D, there are in fact two paths, ACD and AFED. To E, in contrast, there is a single shortest path, which is AFE. The only thing that Dijkstra is used for in this simple context of this use of OSPF is simply to populate the routing table. So at A, we will know in order to go to router B, which is B here, the next hop is probably the interface here, but also the router B. And the only non-trivial thing is in order to go to D, we will see that there are two possible next hops that are C or F, and the distance is the same 30. So that's the only thing that at the end OSPF will need from this complete computation. But the remarkable thing is we're able to have multiple shortest paths if multiple exist here. I mentioned that we use those red arrows to know the path. Now, you can improve a bit the execution time. In the version that I've presented, first you run Dijkstra. Then, in order to know what is in order to know the routing table, we need to go to every destination and follow the red arrows in reverse direction. The true Dijkstra algorithm that is implemented in the routers avoids this last pass at the end. It embeds this directly in the computation, and that gives this code here, which is more ugly and more difficult to understand. But the only difference is that we embed directly the next hop in the computation, so that at the end, when the algorithm has converged, we don't need this additional path. So back to our toy network. This is what will happen at A. A will run Dijkstra on this graph, and we'll have at the end this table. It will know for every destination. The destination is either a router or a subnetwork, because we know that subnetworks are, or they are called networks by OSPF, are also nodes. And then it will therefore know how to go for each of those nodes and what is the cost here. There are a few optimizations that are done. Typically, in a network, there are lots of what is called stub networks. A stub network is like N3 here. That's a network that's connected to a router and leads to nowhere. It's a dead end, if you want. So most networks have a lot of dead ends and a smaller backbone, because by the nature of things, there is more networks at the edge than in the center. That's the beauty of networks. We can spare on the number of links by doing that. So what Dijkstra does is networks like N1, or like N3, sorry, are not done. What OSPF does is that it excludes the stub networks from the shortest path computation, because we know that a network like N3, a stub by definition can be connected only to one router. So what Dijkstra does is compute the distances to all routers. Then it examines all routers one by one after the shortest path computation is done, and adds computes the cost from A to N3 by examining B and all the stub networks that are connected to B. So this is how N3 would come. In fact, it would not come directly from Dijkstra. So as you see, OSPF has a lot of small optimizations like this. I've mentioned 2 or 3 of them. It has a large number of other ones to make the code faster. We have seen that there can be, and there usually are, multiple shortest paths to a destination. If you take a ring, for example, that has an equal cost everywhere, there will be lots of distances that have the same, there will be lots of paths that have the same cost here. Now, assume you are router A, and you have now a packet to send to a destination that is D, for example. What should A do, according to you? Should it use all of them, or should it try to do something smarter? And we see that the majority says A, which is in fact what was done at the beginning of the internet. But there's a problem in doing that. What might be the problem in doing this? Well, remember TCP, right? By doing that, you will reorder packets. The path may have very different latencies. So you will put some reordering, which is okay. It's legal. You're not breaking the protocol by doing that. But you make the job of TCP more difficult. The reordering heuristics that we have found might fail, or might, if we use the reordering window, it will have to compute a large reordering window, so it will have a harder time detecting whether a packet is lost or not. Because of this reason, we try to do something a bit better. We can do it, but in order to improve the performance of TCP, what has evolved over the years is the idea of doing something a bit smarter, which is called per flow load balancing. So the idea is you would like to do this, but it would be nice if you could find a mechanism such that all packets of the same TCP connection follow the same path. So if you have 1 million packets to forward, okay, you should put 50% of them on the left, 50% on the right. But while doing that, please make sure you send all packets of the same flow all on the left or all on the right. How can you do that? There's a very simple way to do it, which is very often implemented in routers. In the routers we have in the lab, this is implemented. We can use a hash function. So we see hash functions everywhere in this course. Here, a hash function does not need to be a cryptographic hash. It is simply some function that takes a string of bits and returns a number between 0 and 1. The string of bit is the flow identifier, as is visible by this router. So this router normally should look only at the destination address. But if it wants to keep all the packets of the same TCP connection together, it has to know they are in the same TCP connection. So it will do one thing that violates the layers, but that all routers do, which is to look a bit in the higher layer protocol. It will look at the port numbers and the protocol type. And if the packet is not encrypted, it's not in a VPN, like we'll discuss a bit later, that gives me access to the flow. So the flow is identified by source and destination IP addresses, source and destination port numbers, and whether it's TCP or UDP. So if you do that, you put together all the packets of the same TCP connection. So M is this bit string, which depending if IPv4, IPv6, can be a few tens of bits to a few hundreds of bits. And the hash function returns out of this a number that is between 0 and 1. If it's a cryptographic hash function, it has to be such that you have no clue which number is returned and why. In particular, if something gives you no information, it has to be uniformly distributed. It has to appear random and be uniformly distributed. Uniformly distributed means if I take 1 million different flow IDs and I apply the hash and I do a histogram, I will see a flat histogram. And cryptographic means it's very hard to forge a collision. So if I want a given hash and I have a hint about the M, I could try to guess it. Here we don't need this. All we need is that the distribution is uniform, which is done by a lot of very simple hash functions that can be computed in a few C instructions. And then the trick is, assume, for example, I have two possible paths. Then I'll compute the hash. If the hash is between 0 and 0.5, I will use the first path. If it's between 0.5 and 1, I will use the second path. So if the hash is truly giving me a uniform distribution of the values, with probability 50%, a flow will be sent on the left or on the right here. This is, roughly speaking, how things are done. And this is called per flow load balancing for equal cost multipath here. And this will be done in the lab unless you disable it. That's a default function that comes with practically all OSPF implementations. Last job of a routing protocol is to be able to react to any change in conditions in the network. Changes occur when you change the network because you grow it or you consolidate it. Perhaps you replace a set of 4 small routers by one bigger one because you have a more powerful LAN to interconnect them, for example, or more often because there is a crash somewhere. There can be a crash of a router. A router is, in some sense, a computer, so like any computer, it crashes. It can be also simply the OSPF process that crashes. But it can be also very often links that die because somebody is doing road construction and we have destroyed a cable. This is a very frequent cause of network outages. What happens when anything changes? Well, first we have the hello or the BFD protocol that will detect that a link is down, because the messages between two routers don't manage to cross that link. Or that a node is down because a router does not respond to the hello protocol or to the BFD protocol. So whenever a router sees that, it sees, oh, the topology has changed. My neighbor database has changed, and I will inform everybody in the network of this change here. Same thing if it's only a link that has changed here. So there will be new LSAs that are sent whenever any router sends that something is new. And of course, LSAs are propagated, they are flooded. If a router receives a new LSA, it's new because it will have a new sequence number, then it will flood it to everyone. And of course, when this happens, the topology database has changed, so we need to recompute the shortest path. In the simplest form, recomputing the shortest path means run Dijkstra again. We will not see that in detail, but in fact, you can do better. If you know that the change is localized in one part of the network, you can run only a delta to Dijkstra, so you don't need to run the complete algorithm. Let's illustrate on an example here. Here is a very simple network, a ring network, ABCD, and those are the routing tables that have been made at all those nodes. For example, if we look at A, we see that in order to go to B, A goes towards this east interface, so the interface on the right here. In order to go to D, it has two possible equal cost paths, east or south here. This is what has resulted from the shortest path computation that we have seen before. Assume the link between A and B dies here. At time t0, it dies, for example, because there's a switch that is providing the local area network and the switch crashed. Then A will detect that at some time. So I'm assuming, in fact, at time t1, A detects the failure. A and B will probably both detect the failure, but things go very fast. All of this happens within milliseconds. So at this time scale, we can assume here in this example that B will detect it only later. So things will have time to happen before the two detections. Again, we find things that we are in a distributed system. We look at them on this slide by saying we see everything. We see A, B, C, and D, and we can push a button on A or B or C. But in reality, this is not how things are. In order to do something on B, you need from A to send a packet. So the things are distributed, and there's a delay any action done by A until it affects B. So we don't have this global view of the network here. We'll talk about philosophies called software-defined networking, where we try to restore the global view, but that's another story. The beauty of networking is when we don't have the global view. So A has detected there is something changed. Its adjacency database has changed. B is no longer a neighbor, and the link that was going here is no longer active. So it will add an update here. It will say, my only interface database is I have a link from A to C that has a cost of 10, for example, and the link from A to B, which was previously in the LSA sent by A, is no longer present. So A sends the information about its new local view of the topology. It's not sending information on distances. It's not explaining how to reach D. It's just sending the information on the link from A to C. So while this happens, we can observe an annoyance here. So while this happens, we see that the routing table, of course, A has updated its routing table. So A now has detected that B is unreachable. This is, that the direct link from A to B doesn't work. But since A has this topology database, the one that's written in pink, it reruns Dijkstra, and assuming that happens very fast, you will know in order to go to B, I have another path that goes via C. So I go south in order to go to B. And my alternate path to D, I had two paths before, I have to delete it. So this is the view that A has of the network, and this is, in consequence, how A will route packets. Any packet, in fact, that has to be routed by A will be sent to C. But this has not yet reached C. So what can happen in between? Well, routing loop. If C has a packet to send to B, for example, we see that C has two equal cost paths because it still has the old value. So C will send the packet with 50% probability, perhaps, to A. And this packet now will reach A, but A is in this state, so A will send it back to C, and C will send it back to A, etc. We have a routing loop. The packet will consume a lot of the resources until what happens? Until time to leave or hop count expires. Yeah, so fortunately, this will not last forever. Also, fortunately, sooner or later, C will detect the thing, but we are exposed to what are called transient loops. This can happen in networks of this kind. So there is a time for the information to propagate, and while the information is being propagated and processed everywhere, the network may be in an unhealthy state. You might lose connectivity. For example, if the hash function is such that your flow from C to B goes to A, then you lose connectivity to B. Of course, this will not last very long because C will receive the topology update from A, so it will update its topology, and it will flood it also to the rest, so D will also receive it, and D, as well as B, will receive this new information. Now, what might have happened in parallel, that B also knows that the topology has changed, that it has lost the link to A, so it will pass the information to D, which, depending on which message is received first, might be redundant or not for D. So after this has happened, and if there is no failure in between, all routers will have this new topology database, and they will update their routing tables accordingly. So this is how OSPF will take care of failures. Quick question to check your understanding. And the majority says A, which is probably what will happen. So B is incorrect. So the hello protocol allows a router to know that the neighbors are dead, but if a remote node is dead, it will learn it indirectly via the gossiping protocol, which is answer A. There is a timeout also in LSAs, so this could also, in rare cases, be the way by which you detect the loss of a node because the information sent by this node has not been refreshed. But in principle, it's more likely that A will give you the information first. A few words about security. If you are able to participate in the OSPF protocol for an attacker, then it's wonderful because then able to send information that will say, for example, that the link is down, so you might manipulate all the paths. So you might send invalid routing information that at the minimum may kill the network. But more severe, you might change the network paths to force the traffic to go at some place where you could do some deep packet inspection, for example, to acquire some information, hoping that some of the things are not encrypted or are using weak encryption that you can break. So OSPF uses authentication. In the lab, what we will do is we don't use very strong authentication. We require that you have a password to participate in all the nodes know a password. The strongest authentication that exists in OSPF is this one, where it adds a signature in the form of a cryptographic hash, now a true cryptographic hash, to all the OSPF messages. And this requires that all the OSPF routers have secret keys, and there is one secret key per link. So remember what link means seen from the IP layer. A link is a subnetwork. So if two routers are connected by a point-to-point link, those two networks have to have a shared secret, a secret key, which is the key of the link. If 5 routers are connected to the same local area network, then the 5 routers need to have the secret key that corresponds to this local area network. How you manage the keys is a nightmare, and it's part of the problem. So you need special software that itself will have keys to distribute the keys in the different routers. We won't go into those details here. We will just mention what you do once you have a key. Once you have a secret key, you can make sure that you sign all the messages by when you send an OSPF message. Then you will use this message plus another sequence number, a cryptographic sequence number, which is not the same sequence number as is in the OSPF packet. An OSPF message, a link state advertisement, for example, has a number that identifies what is the round in the sense of OSPF, in order to know whether it's a new message or an old message. Here, the cryptographic sequence number is to avoid replay attacks. An LSA is transmitted by router A to router B, but the message may be lost. It's not using TCP, so it might be lost. If it's lost, it will be retransmitted. When it is retransmitted, it is the same LSA number. It's the same information that we're trying to propagate further. But if it is retransmitted, it will have a different cryptographic number. So that an attacker that has recorded the message, if you play it again, you would not be able to, it will be detected because the sequence number must be updated. If you play it again, if you received it already, you know it's a duplicate, it's an invalid duplicate. So all this information, including also the source address of the router that is sending you this information, is put into a hash, and the resulting 256-bit word is sent also in the OSPF message. So if you're a router, you receive such a message, you can verify by taking the message here, the number that are sent in the clear, whether it comes from somebody that has the secret key. So if you want to attack an OSPF network, the thing you need to know is you need to have access to those secret keys. Small details, this cryptographic sequence number contains a part that survives crashes. So when what happens with routers or with servers in general is that it's quasi impossible to have a server that will work for 3 years without ever rebooting. Right? So you will once in a while need to reboot it, or they will reboot for you because it will crash. So what you do in such cases is, well, what do you do with the sequence number, right? And an easy attack could be take advantage of crashes if the sequence numbers are the same. So hopefully they're not the same, because the OSPF specification says that this should be written to permanent storage, to disk typically. So whenever you reboot, you upgrade, you add +1 to your reboot counter, and all your sequence numbers will be different from the last time you rebooted. For that, you need very large sequence numbers. I'm not sure about the number, but they're probably 64 bits here. So that's you need a huge sequence number space to avoid any replay attack. With what we have seen today, we're able to run OSPF in what is called a single area. And this is the only thing we'll do in the lab. That already will make you a virtual and mini-net environment that will have a number of routers and will keep you busy. In reality, this flooding idea, which looks very nice, is a bit primitive, and if you think about it, not very sophisticated, and obviously it doesn't scale. It is less sophisticated than distance vector, though it has a number of practical benefits that make it preferred today. But one of the major drawbacks is if your network is huge, you flood all information to all routers. So imagine you're a company that has a worldwide router, IBM, for example, right? Or Microsoft or whoever, Google. Imagine you use OSPF, as we said here, with a single area for all your routers. Whenever there is a crash of a router somewhere in Australia or in China or in Greenland, you update the topology database. So everybody floods those information. So obviously, this will not be very efficient. First, you flood a lot of information that is probably not very relevant to everybody. If you have a link between two servers in Tasmania that has broken, so you need to take the backup link, which is also in Tasmania, you don't need to inform the rest of the Google network that this is happening, because the rest of the world is not impacted by this. You will still continue to route packets towards Australia the same way. So you don't want to propagate all information to everyone all the time, given that most networks are not random graphs, but they are structured graphs. They have a hierarchy, they have a backbone. In order to go from a continent to another, you use the backbone, you don't use arbitrary edges that are drawn from the graph. So if you had arbitrary edges, perhaps link state would be not more expensive than anything else. But since it's not the case, it's better to organize things with a hierarchy that corresponds also to the routing, to the paths that are taken. So very large networks use OSPF with a hierarchy that has two levels. So very large networks are typically organized with a backbone. For example, if you're Google, you have routers that interconnect the different main sites that you have. And then within each main site, you have your own area that is connected to the backbone, hopefully by at least two routers, so that you have some redundancy. So this is what OSPF supports. So OSPF uses a system of areas. It's a not very sophisticated hierarchical system. It has only two levels, but so far people have found it sufficient. And the terminology is that the backbone area is called area 0, and one of the rules is that traffic, so packets that go from one area to the next, must go via the backbone area. So you're not allowed to have a direct link between A2 and B2, because we would not know whether this link belongs to area 1 or to area 2. So every inter-area traffic goes via the backbone. If you impose this discipline, then it's very simple to run this hierarchy of areas using the following principles. Inside one area, we use link state. So exactly in the way we've explained before. So inside area 1, all the routers flood all new informations and compute shortest path using Dijkstra. Now, some routers must belong to both the backbone area and the peripheral areas. They are called area border routers. Here it's X3. There are two X3 here, so X1. So the numbering is wrong. So those 4 X routers here belong both to area 0 and either to area 1 or area 2. And when they belong to both area, they do the two link states. So inside area 0, we run one instance of link state, one instance of flooding, one instance of Dijkstra in every router. And a router such as X4 belongs to two areas, so it has two flooding protocols. It belongs to the two. And the routers that are at the border, they are the ones that are used to inject the information from one area to the other. Everything they learn in one area, they use it and inject it to the flooding mechanism of the other areas. So let's see an example. Here the numbering is correct, so we have those 6 routers in the backbone, and we have 2 non-backbone areas, and I've put values of the distances here. So if we look at area 2, for example, in area 2, all 4 routers run the gossiping protocol, and I have this vision, which is the topology database, which is thus the picture of area 2. Of course, it's a very simple example here. There's only 2 stub networks, N1 and N2. All routers here have this topology database and are able to compute their distances. In particular, X4, using this map and Dijkstra, can compute its distance to N1. So N1 is this one. We see there is, if X4 runs Dijkstra, it will add first X6, plus then it will add B1, and therefore it will find the distance to B1 is 9, and the distance to N1, which is a stub network, is 9 plus 1 is 10. So the distance from X4 to N1 is 10. So X4 does the same to all networks, and all routers, including X6, do also the same. So we find those distances. This is using exactly what we have seen a few minutes ago. This is the normal operation of link state with flooding and Dijkstra. Then next step, X4 and X6 are also in area 0. So they will add this distance information that they have learned from area 2, they will add it in the topology database of area 0. They will do as if they would be directly connected to N1 and N2 with the costs that they have computed. So this is illustrated by the things in yellow here. So this router knows it is at the distance 10 of N1, so it will do as if it's directly connected here. And it will flood that information using the link state advertisements, using message of a different type. As we will see in the lab, there are lots of different types of messages. One of them is called a summary advertisement. It's a summary because it's not first-hand information. It comes from the result of Dijkstra in area 2. So as a result of the flooding here, all areas in the area, all routers in area 0 have this vision. So for example, X3 knows this. So now X3 can use this to compute its distance to all those prefixes using the same thing we do when we have stub networks. We can consider that, so X3 knows its distance to X4, for example, which is a border area router. So it will use this formula. My distance to N1 is the minimum of my distance to a border area router plus the distance from this border area router to N1. So if I do that over all border area routers that are connected to N1, which are those 2, I try those 2 distances and I take the minimum. This formula is called the Bellman-Ford formula. That's the formula that's in fact used by distance vector routing protocol. So we see that OSPF mixes in fact 2 routing formulas, Dijkstra and link state, inside an area. And to put all the areas together, it uses something that looks a bit like distance vector. We'll see more details of a distance vector here. Right now, all we need is to use this formula. So this formula is not rocket science, it's the obvious thing. Right? You are in area 0, you wonder how to go to N1. You know, some border routers in your area have a distance to N1. Then you try all of them in sequence, and you say, and you look at the one that gives you the shortest path. Here. For example, X3 will do this computation. It will find 2 possible paths. Path will give 23 and 34, so the distance will be 23 here. So its distance at X3 will be 23. This can be used, it gives not only the distance, but we don't care so much about the distance. What we care is about routing. And the principle of Bellman-Ford is for routing, if we remember not only what is the minimum, but also which branch gave us the minimum, we know that the minimum is obtained by this first branch here, if we go via X4. So it means that this router will remember not only the distance, but in order to go there, we need also to go to X4. How to go to X4? We know this by the link state mechanism inside area 0. So X3 will do that, will update its routing table, and now X3 knows how to route a packet towards N1. It knows it has to go via X4 here. Now, X3 also belongs to area 1. And X3, through this Bellman-Ford complement to the Dijkstra algorithm, knows also the distance to N1 and N2. So inside area 1, now it's recursive, the same thing that has happened before, exactly the same happens again. Now X3 knows a distance to N1, and the distance is 23. So it will pass this information, again as a summary link state advertisement, into the link state database of all routers in area 1. So there will be this map in area 1. Same principle as before, but of course the distances are different. Now in area 0 we had the information given by those two routers, 4 and 6. In area 1 we have the information that's injected by router 3 and 5. And all routers in area 1, including A1, for example, will use this information and will use the same formula. So A1 will find that the distance to N1 is 33, and that the shortest path is via X3. So it will look up in its routing table what is the next hop to X3, and this is what it will write in its routing table. So this is how OSPF works in reality when we have multiple areas. A quick question to test your understanding. There is an improvement, but the majority says B, which is not the correct answer. So A1 is here, is in area 1. From area 1, it knows this map here. This is what it knows. So it knows the distance from this map. It will know what is the distance from the border router to N1. This is the yellow things. So it will know this from the link state database. The distance from itself to the border area router is not in the map, but it's in the result of the Dijkstra computation done in the area by router A1. So the correct answer is A here. This is incorrect. The distance from BR to N1 is not in the routing table. The routing table at A does not have the distances from a third-party router to a destination. It only has the distances from self to everywhere. It's information that is not about yourself. It can only be in the link state database. It's not in your routing table. How many link state databases? So that was an easy question. Of course, it's 2. B is a border area, X3 is a border area router. It belongs both to area 1 and area 0. And that's the max you will see in a router in OSPF. You cannot belong to more than 2 areas. You can be only a border area router if you're in area 0 and a non-area 0, in a non-zero area. There is a large number of other details that we won't see in OSPF. You will see enough in the lab, I'm sure. In particular, one, as usual, there are easy things and more difficult things, which are OSPF is very simple because the way it puts all the errors together is very simple. You could imagine a more intelligent way of putting errors together by saying, I put areas by grouping things together, then I interconnect them by arbitrary links, and those links might be anywhere. So I could have not necessarily something like we have here, where everything in the center has to be area 0, and every communication from non-area 0 to non-area 0 has to go through the backbone. This is what makes this system very simple. We don't have recursive things. We don't have loops. We propagate the information only in 2 steps, from area non-zero to area 0, and from area 0 back into the other areas. This requires that area 0 is able to connect all the different routers together. So there is a large amount of code complexity for handling what is called area partition. If for whatever reason your area 0 is broken, you need to work very hard to make it still work. So there's a number of tricks that we will not see. But that explained some of the complexity of the practical implementation of OSPF. Voilà. thank you very much. That's all for today. For the rest, we will discover in the lab the practical complexity of OSPF.